Okay, welcome guys. This is Mr. Ndabezita once again, and we are now in 1.2 in our calculus 13th edition by George Thomas. So we are looking at combining functions, shifting these functions, and scaling the graphs. So we will look at sums, differences, products, and the quotients of these functions as they undergo the transformation that we have in there. So they say, like numbers, functions can be added, subtracted, multiplied, and divided, except where the denominator is 0. We know that, to produce new functions. If f and g are functions, there's a relationship that is happening where one value of x is mapped to exactly one value of y, because that's what we looked at thus far. Then for every x that belongs to the domains of f and g, and that is for x is an element of the domain of the intersection of f and d, we define the functions f plus g minus product by the following formulas. So that is just to say you can have a first function and then you add a second function to that. So we can just continue in this. I'm sorry, I was just disturbed. So what we are doing here is just to multiply. Remember, these are functions. We are adding these functions. So you have f at x plus g at x, there it is, and then the difference is f at x minus g at x, and this is the product of the two functions. And then they say that notice that the plus sign on the left hand side of the first equation represents the operation of addition of functions, whereas the addition on the right hand side of the equations means addition of real numbers f at x and g at x. I think this is very important that we note that. They say notice that the plus sign on the left hand side of the first equation represents the operation of addition of functions. Very important. Whereas the plus sign on the right side of the equations means the addition of the real numbers f at x and g at x. At any point of the domain where f intersects with g, at which the denominator or the g at x is not equals to 0, we can define the functions f divided by g by the formula that is provided there, provided that the denominator function is not equals to 0. So functions can be multiplied by constants. If c is a real number, then the function cf is defined for all x in the domain of f by c f at x equals that. So we are just multiplying the function with a constant value. Now we have an example. The functions defined by the formula f at x equals the square root of x. Do we have such a function? Is it drawn? No, it is not. Let us just go quickly to draw that. So we can just come here and we can just try to draw this function. So let me just put this over here. I have insert a function. So what I will do is just to say x to the exponent of 0.5, and I can have a function like this. So let me just come here and just pull it to this side. So we have this function. This is how it looks like. And then we continue in here. We have this and we have that. So let me also draw up that one. So I'm just going to come here and I'm going to say 1 minus x raised to the exponent of 0.5, and I'm going to use this, and the color will be let me just try to use red, and we have this function. Let me just check whether this is correct. 1 minus x, so we have 1 minus x. Yes, we have it. There it is. So these two functions have the domain. So the domains of f is 0 is to positive infinity. Let's just see. There it is. This is correct. And this one is 1 is to positive infinity. Let's just verify that. 1 is to negative infinity. There it is. And then the points common to these domains are the points 0 is to positive infinity, the intersection of negative infinity is to 1, and this is the intersection, the point common on both 0 and 1. Let us check that. 0, when x is 0, y is 1, so they say so. So the points that are common there, so this would be the intersection of the two. So 0 is to positive infinity is for the first one, minus infinity is to 1 for the second one, and then we find the intersection of the two. And algebraically we can find that, but they have done it for us. Here the intersection point is 0 and 1. When x is 0, y is 1. So when x is 0, y is 1. So they tend to say to us that this is the intersection, but for us it doesn't really look like that. It looks like when x is something like 1/2, y is also something similar. But okay, that is fine. But let's see whether our graphs are correct. This one, negative infinity is to 1, and it is true, negative infinity is to 1. There it is. So we have drawn these functions correctly, but when it comes to the intersection, I honestly do not see this 0 is to 1 as the domain of those functions. Because remember, they say to us f plus g, when you are adding these functions, this would become the domain. So the domain of f intersecting with the domains of g. And let's check the values of x that intersects the values of these functions, the value of x intersecting with the value of x of that function. So to me it looks like okay, let me just try to draw this using an interval. Let me try to use an interval. Let me just say from -3 is to 3, and let me also go to this one and just use -3 is to 3, and we have that. So let us go back to our reading here. They said to us now, notice that the plus sign on the left hand side, so we have the left hand side, the plus sign on the left hand side of the first equation represents the operation of addition of functions. Here it is. The plus sign on the left hand side represents the operations of additions of these functions, whereas the plus sign on the right hand side of the equations means addition of real numbers. So this time this deals with the addition of real numbers, which numbers, the real numbers on the function f and the real numbers on the function g. So that is why when we come here, the domain, remember, on the left hand side this is the operation, but on the right hand side the addition sign deals with what? Sorry, the addition sign on the right hand side of the equation means addition of real numbers. So this deals with the addition of real numbers, the addition of real numbers. So this side is the operation, this side is the addition of real numbers. So we have this domain of 0 is to 1. I think I need to show you something. Okay, let's do this. Let me just go to a WordPad so that we try to understand this. I don't want us just to assume that we understand. I actually want us to understand this. So let us look at something. We have a function. Let me just place this in here and let me do this. So we have the square root of x. So what I'm going to do there is, I know that the domain here is that x should be greater or equals to 0. Very important. And then secondly, I know this one, that 1 minus x should be greater or equals to 0, and I can solve there and say minus x should be greater or equals to minus 1, and then when you divide both sides by negative, the inequality reverses so that x is less, or sorry, let me do this, so that x is less or equals to 1. Right, so that is fine. So what I have here are the values of x that are greater than 0. I'm moving to the right. Values of x that are less or equals to 0. I'm moving to the left. So you see where that 0 and 1 comes from. This is where it comes from. The intersection of 0 and 1. There it is, 0 and 1. Very, very important that we see that. Okay, that is fine, no problem. We now fully understand what is happening, and then we can also investigate for many functions that we have in here. So I was thinking maybe it is possible. Let me just try to do this. Let's try to draw them on the same, just to see whether we can get that. So I'm going to come here and I'm going to have two functions at the same time. So I'm going to say x to the exponent of 0.5 plus, and I'm going to have 1 minus x to the exponent of 0.5. I'm trying to combine these functions, and I'm going to draw this from minus 10 to positive 10, if it will be possible. And when I try to do that, this is the function that I find, and this function that I have doesn't really show me exactly what I want, so we might just as well just leave it. But we understand what is happening there. We understand exactly how they found that. And then here is the difference. So this is the operation, and we know that this subtraction was found as a result of adding the two functions. And we have read that in theory, that, okay, the addition on the right side of the equation means addition of real numbers, so we are just adding those real numbers and we are getting the same domain of those the domains of f intersecting with the domains of g. It's 0 and 1, the same in there, the same will be there. And for subtraction, and then even if you can swap this, as you can see, you can say f minus g at x, or you can say g minus f at x. You would still have the same thing. The domain remains the same. Even when you multiply in here, we know that the square root of x multiplied by the square root of 1 minus x, so this is just the same as doing what? Remember what we are doing here, this function multiplied by that function. So what we simply do, we just take one square root and we multiply the inner functions that are inside of the square root, or the numbers that we find inside of the square root. So for example, let us just come here. When you have I don't think this will do what I want. Let me just try to find something different. Let me just try to find something different so that I can demonstrate what is happening here. So let me just okay, let me just do this. Remember, when you have the square root of 2 multiplied by the square root of 4, this would be, okay, I could have just used a calculator. I could have just used a calculator, because what I can do here, I want you to notice something. The square root of 2 multiplied by the square root of 4, and it will give you 2 the square root of 2. What has really happened here, you just have one square root, then you can just say 2 times 4, and it will give you exactly the same answer. So this is exactly what has transpired here. We just introduce one square root and then we allow this to multiply with that, and we get that domain. Okay, that is fine. And then the quotient also deals with this. F divided by g has this domain, and x equals 1 is excluded because it is not defined. As you can see, that the denominator cannot be equals to 0, so x should not be equals to 1, and here x should not be equals to 0. So this is just basically what we are learning from that. So we drew this function and we found it in here. When we drew that function, and I showed you that function, but it wasn't just the right time to be there. I showed you that function when I said x to the exponent of 0.5 plus 1 minus x to the exponent of 0.5. And let me just use a black color for that. Let me use a solid line. I showed you that function. Here it is. Now let us try to see what is happening there. So I'm just going to take this and just place it on the side here. So I have combined two functions in here, and let me just zoom in so that you may see what is happening. Let me just place it somewhere here, and this is what we have. All right, so they say combining functions, shifting and scaling of these graphs. So we have that. Okay, I can also draw them individually. That is also fine, so that we can have that which is drawn for us there. 0.5, sorry. Let me just use some different colors. Let me just use red, and we have that. Let me have another one, and I can just have 1 minus x to the exponent of 0.5. Let me use a different color and have that. So we have exactly what we are seeing there. So this is what we have. So what is happening here? The domain of the function f plus g is the intersection of the domains of f and g, and the interval 0 is to 1. Very important, 0 is to 1, 0 is to 1. So this is the intersection of the two. Is it true that they are intersecting there? Yes. Look at that intersection. Because of this graph, I cannot say they intersect here. Look now, this function is not defined there. But at this point, we need to be very careful here. We need to be very, very careful here. Look here. Look what is happening here. When x is 0, y is 1. We are therefore saying the domain of f and g is the interval 0 is to 1. So when x is 0, y is 1. Right, on the x-axis where these domains overlap. Very important. Now let us look here. Do these domains overlap at 0 and 1? We need to look into this. So when x is 0, y is 1. And this is y equals f plus g. There it is, the combination of the function f and g. And we have it in that way. And we have this function, there it is, y equals the square root of x, and y equals the square root of 1 minus x. We have this. Okay, that is fine, no problem. And then secondly, what is it that we are having? This interval is also the domain of the function f and g. So what we are seeing in here, let me just fix this. Okay, let me just do this. 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 So this is what we are having. Therefore, we are saying the domain of the function f plus g is the intersection of the domains of f and g. So I showed you a simple way when we were using Notepad as to how to find those values. And with a Notepad, please remember, because we have this function, the square root of x, we have the square root of x. Therefore you will say x should be greater or equals to 0, and here you will say 1 minus x should be greater or equals to 0, and you will find the domain of both, which will be 0 and 1. We found that, and they are both inclusive because we have greater and equal or less and equal, so they are both included, those values that you found as 0 and 1. Very important that we try to understand that. So the intersection will be the domain of both those functions. And then we go and look at composite functions. Composite is another method of combining functions. So if you do not want to have this arithmetic way of combining functions using addition, subtraction, multiplication, and division, we can use composition. So composition is another method of combining functions, and let us just have the definition. If f and g are functions, the composite function, which is denoted by this open circle, which is the fog, f composed with g, is defined as what? is defined as defining the function g inside the function f. The domain of fog consists of the numbers x in the domain of g for which g at x lies in the domain of f. Okay, the definition may be a little bit confusing at the start. I'm not going to use those diagrams to explain this. I think this is best explained with the examples. So we have f at x equals the square root of x and g at x equals x plus 1. Then they say to us find fog g, f composed of g. Now remember how this works. I'm going to use this in order to explain this. Let me just do this. So I'm going to show you with this software what this really means. So we are here. Let me just do this. Let me just do that. So we are having a function which is the square root of x and g at x equals x plus 1, and we want to find fog g, so defining the graph of g inside the graph of f. So the first thing that you do, what is the graph of f? It's the square root of x, right? This is the function f at x, and you want to define g at x inside of this function. Now what is g at x? G at x, it's equals to x plus 1. So this is g at x, it's x plus 1, right? So I want to define this function. Let me do this. I want to define this function inside of that function. So how does that work? Inside of f, where you see x, you write x plus 1. So here I have x, which is my function f, and where I see x, I'm going to write inside of this function, where I see x, I'm going to write x plus 1. So I see x, I'm writing x plus 1. So what is this now? This is equals to f g at x. So you have defined the function g inside the function f by doing what? Where you see x in f, you write what g is. This is exactly what we have. So they will find that answer of the square root of x plus 1. And this is the domain. The domain is -1 is to positive infinity. This is the domain. So let's go in here, and then instead of drawing both graphs, I'm going to draw that graph. So please allow me to delete in here, delete in there, and also edit this one. So I want to have that function, which is x plus 1 raised to an exponent of 0.5. And let me see how it looks. This is how it looks. Now let us see whether the domain is true. Look, -1, and it is defined at -1. So you will have that enclosing bracket. -1, where is it heading? Towards positive infinity. So this is exactly what is happening. And then we can have, now we are defining g inside of f. Now let us check that. This time we are defining g. Now we want g, and we want to define f inside of g. Right. So this time I want to define the function f at x. Okay, let me just use a small letter here. I want to define f at x inside of g. So the first thing I will do, I will write g. What is g? Remember, g at x is equals to x plus 1. Sorry, x plus 1. So inside of g here, where I see x, I'll be writing the square root of x. So now g of f at x is equals to, I see x, then I'm writing the square root of x plus, and then I'm having my 1. And there it is. And now let us investigate the domain here before we can even go and look at the answers. So I'm going to edit this one. Now I'm drawing this function. So what I will just simply do, I will just say x to the exponent of 0.5. This is the function. Just to ensure that I don't make a mistake, I'm going to do this. And I'm going to say plus 1. And let me draw that function. Now look at how that function looks like. So the function is defined at x is equals to 0. So the domain will be 0 inclusive is to positive infinity. And let's see how Thomas sees things. 0 included is to positive infinity. And let me just, cancel. And what we have is that. What we have is that the square root of x plus 1. So we can also define f inside of f like that. Let me just show you how that works. So we can just come here and we can define f inside of f at x. So we are defining f inside of f. So the first thing that I'm going to do there is to write the function f. And I think f was given as the square root of x. So you will have your square root of x. There it is, which is f at x. There it is. So inside of f, where I see x, I'll be writing the square root of x. So let me just say, now I have the square root. Now inside here where I see x, I'm writing the square root of x. So I will have the square root of x. And this is what I have. This is what I have. And I can simplify this. This can be simplified. And how can I simplify that? I can leave what is inside. I can leave this. I'm going to say the square root of x and remove the outer square root by having an exponent of 0.5. This is what I can have. And now I can work on this one. Equals. Now I want to remove this square root. I can leave what is inside of the square root, which is x, and I can rise this. When I remove this square root, I have 0.5. But all this is inside of 0.5. So I'm going to come here and do this. Good. And then I'm going to raise this to 0.5. Good. And then what I'm going to do now is just to multiply these ones. So I'm going to have my x, and what I will do there is just to say 0.5 times 0.5. That would give me let me just do this. Let me just do this. 0.5 times 0.5, it's 1/4, because 1 times 1 is 1, 2 times 2 is 4. So I can have this and I can draw that function. Let me just edit this one. So what I can do, I can draw that function. And how do I draw that function? Now remember, I have x to the exponent of let me just say 1 divided by 4, and let me draw that, and this is what I have, provided that I have drawn the correct graph, and the domain would be 0 is to positive infinity. Let's check how Thomas sees things. So we can come here, let me just do this, and let me just do that. So we are correct, there it is, and 0 is to positive infinity. Did we find that? Yes, 0 is to positive infinity. So these things are not that complicated if you understand what is happening. And let's just investigate the very last one, g gog of x. So g, defining the graph of g inside g. So let's just quickly try to look at that one. Alright, so let me just do this. I know that this is g at x, so I have g at x, which is equals to x plus 1. Right, now I want to define g inside of g. So where I see x, I'll be writing x plus 1. So I see x and I'm writing x plus 1, but there's a plus 1 again. There it is, which will simplify to x plus 2. Sorry, because these are like terms. And I can draw that graph. I can have the function of x plus 1. So I can have x plus 2. Sorry. And I can have it in this way. And what is the domain? Negative infinity is to positive infinity. But I can specify the interval also. The arguments I can say from -3 to 3. But when you do that, okay, let me just do this. From -3 to 3 to 3. Okay, it still doesn't want to do that. Okay, let me just say from -1 to 1. Yes, so please be careful when you specify the interval. Please know, okay, let me just do this. Let me do this. Let me show where it starts and where it ends. So you see it's still continuing. Please, when you specify the interval like this, please do not say the graph begins at -1 and end at 1. Please, you have used an interval here. This function continues from negative infinity to positive infinity. And let's just see what Thomas has for us. And this is exactly what we have. So guys, I'm just going to pause it here, and in the next tutorial, okay, just in a few minutes we will continue. Let me just say in a few minutes. So let's just have a pause for now. Okay, let us continue, guys. Let us try to continue. So we have dealt with that, no problem. We saw that. To see why the domain of the fog is -1 is to positive infinity, I notice that g at x equals x plus 1 is defined for all real x, but belongs to the domain of f only if x plus 1 is greater or equals to 0. That is to say, when x is greater or equals to -1, we know that. Notice that if f at x equals x squared and g at x equals this, the fog will be equals to that, which is equals to x. However, the domain, okay, let us try to look into that. So if we have f at x and g at x like this, so let me just get rid of all this. So let us have g at x, which is equals to the square root of x, and f at x, which is equals to x squared. Okay, we have this. Now what is it that Thomas wants? The fog. So we want f o g. So this is what we want. We want a fog. And then how do we calculate that? So we are defining g inside of f. So first of all, we write f, which is x squared, and then from there, let me just use a pointer like this. And then from there, remember this is the function f, so we are going to define g inside of f. So inside here we have f, there it is. So where we see x, we'll be writing the square root of x. So here I see x, and I put in the square root of what? Of x. But remember this is squared, so I just raise this to an exponent of 2. But do not forget that this can be simplified. So what we can do there is to leave what is inside of the square root and then remove the square root. This is 1/2, which is, okay, let me just write it as a fraction for you. 1/2, there it is. But do not forget something. This is raised to an exponent of 2. Please do not forget that. And we can show with an arrow once again. So 1/2 times 2 is 1, so you are just left with x. So this is exactly, I think, what Thomas should have found. You are just left with x. So let's look at the domain. Let's try to draw up that function. Let us try to draw this function. Y is equals to x. And I'm not going to specify the interval there. And look at the domain. And I want to show you something. Negative infinity is to positive infinity. He says, however, the domain of this is 0 is to positive infinity and not minus infinity is to positive infinity, since the square root of x is required, or the square root of x requires that x be greater or equals to 0. So the best way to never and ever make this mistake, please, the best way to never and ever make that mistake is to check individually first. We know that this function is not defined for x is negative. Please, it is very important. So in order to have the intersection of the two of those domains in here, please be very careful here. What we can do is this. Let me just go to a WordPad. There it is. Now remember, we have the square root of x. Okay, let me just do this. Let me just copy this and paste it there. Okay, I'm trying to copy this and I'm trying to paste, and unfortunately I can't do that. But remember, we can solve this by saying that x should be greater or equals to 0. Very important there. And then we know this function. which is just x squared, and I know that x squared is defined on the real line. So what I can do there, if I want to find here the domain, I know that the domain is from negative infinity is to positive infinity, but to accommodate this one, it is only defined when x is greater or equals to 0. So I will have to say the domain is 0 is to positive infinity, because it is not defined when x is less than 0. So that is why in here Thomas is stressing very much that we be aware of this. Okay, I hope we have understood that. Now shifting a graph of a function. A common way to obtain a new function from an existing one is by adding a constant to each output of the existing function or to its input variable. The graph of the new function is the graph of the original function shifted vertically or horizontally as follows. So I can have a function. For example, let us make a demonstration here, but I'm going to use a function that can show us this. So I'm going to use a parabola squared. So suppose I have this original function and I want to shift this function's vertical shift, either going up or down. So for going up you add a positive k, for going down it's a minus k, hence we have the modulus here. Shifting the graph of f upwards, k units if k is greater than 0, if it is positive it goes up. Shifting it down, the modulus of k units if k is less than 0. So let me just come here and try to move this graph vertically upwards by just adding a 3, and let's see what will transpire. The graph goes 3 units upwards, and I can take the function down by using a minus 3, and the graph will go 3 units downwards. So this is, so you are just adding. You have a function and then you are moving the function up or down by adding a constant, positive or negative. And then we can also have a horizontal shift, taking the graph maybe upwards to the left or to the right. And then how do we do that? So this is how we do it. Shifting the graph of f left units h is greater than 0, and right units h is less than 0, like this. So how do you do that? You go inside of a function, let me do this so that this is very clear. Let me just do this. So what I have is just to say x squared. So I will have my x squared, let me do this. I will have my x squared plus 1. So let's see if this will work. Remember, we are not taking the graph upwards or downwards, we are taking the graph left or right. So it didn't work. This is not the right way of doing this. So I have my x squared, there it is. So what I need to do, I need to come in here. So let me just remove this. I need to come in here and say minus 3. Let's check if it will work. Now I want you to be aware of something. Now let me draw the original graph so that you can see exactly what I have done here. X squared. Here we are. So here was the graph, and the graph was shifted 3 units to the right. And how did I do that? Sorry, not this one, that one. So shifting the graph 3 units to the right, this is how we do it. This is exactly what Thomas is trying to show us here. We can even move the graph 3 units to the left by saying plus here, and the graph will move 3 units to the left. So this is something worthy of noting, very much worthy of noting. Scaling and reflecting a graph of a function. Okay, that is fine. To scale the graph of a function y equals f at x is to stretch or compress it vertically or horizontally. This is accomplished by multiplying the function f or the independent variable x by an appropriate constant c. Reflections across the coordinate axis are special cases where c is equals to -1. So okay, that is fine. We have translated the graph, the original function 3 units to the left and 2 units to the right. We have translated the modulus function 2 units to the right. Okay, that is fine. I'm not going to do a lot of work. So reflection, y equals minus f at x reflects the graph of f across the x-axis, because if you reflect across the x-axis, only the value of y changes the sign. Reflecting the graph across the y-axis, only the value of x changes the sign. And I'm not going to deal with that. And I'm not also going to deal with this. This becomes very simple. What we are going to do in the next tutorial, let me just check. Okay, let me just go through a few things just for clarity purposes. Okay, let me just do this here. Vertical and horizontal scaling and reflecting formulas. For c is greater than 1, the graph is scaled. Y equals, you take your function and then you multiply that by a constant. And then what does that do? It stretches the graph of f vertically by a factor of c. Vertically. So it stretches the function vertically by that. And then when you have this fraction, it will compress the graph of a function. Let's see this. I think we can investigate that. So let me come here. Let me just get rid of this. And let me just come here. And when I'm here, what is it that I want to do now? I want to stretch the graph of a function by a certain value. And I want you to note what is going to happen here. So this is my function. Let me do this so that you can see. This is my function. And in this function, I want to multiply this function by 2. And look what is happening here. Look before I multiplied by 2. I want you to note what happened here. Before I multiplied by 2, this was the function. It was opening up. And then when I multiply by 2, the function is compressed. And when I multiplied by 3 or maybe 5, it becomes even and more compressed, and so on and so on. In the case of a parabola, because it stretches the graph vertically by a factor of this. For c is bigger than 1, and I have used a value that is bigger than 1. Alright, and then let's use some fractions and see what will happen here. So let me just use here, I'm going to use 0.5. And I want us to notice what is going to happen. You see, so in the case of a parabola, when c is greater than 1, it compresses the function. When c is a fraction, it widens up the function. The function stretches the way it should. Okay, guys, I will be back. Just give me a few minutes. Alright, let us continue in this. I think, guys, this is best explained. Now, remember, we looked for the scaling where the value of c is greater than 1, but I also included the values that are less than 1, like half and so on. In the case of the parabola, I just wanted us to do that quick investigation as to how that would affect the function. Right, and then even with one function as a fraction, we can see that. And then if you now take the value and you are multiplying this constant by your function there, it compresses the graph of f horizontally by a factor of c. So let us try to check whether that will apply in this case. So suppose I have a parabola x squared, and now what I do inside of this function, this is my function, it's x squared. I have my function y equals x squared, and I multiply that by a factor, let me just say 2. Sorry, 2. So let us see what will happen there. This is what we have. Let me draw the original function so that we can see the differences. So let me just have x squared, and let's see. You see, this is x squared and this is 2 times x squared, so it will compress it. Now let's find out if that is true. Compresses the graph of a function f horizontally by that. So is it compressed horizontally? Yes, it was compressed horizontally from this to that, so it will be compressed in that way. And you can look at you can divide by this and check what is happening. We are not going to do that. And this is the reflection, and we have these reflections there. So you have the original function, and then you are multiplying by a value there, 1/3 of this. This is how it looks like, and we can draw these graphs and we can find out this, and many of this can be proven right or wrong, so I'm not going to stress so much in that. Example 5. Given the function x4 minus x3 plus 10, find the formulas for compression of the graph horizontally by a factor of 2 followed by a reflection across the y-axis. So suppose we do not have these answers here, but we have read and understood what is happening. Compresses the graph horizontally by a factor of 2. And this is what we saw. So let me just do this. And I'm not very sure if this software will be able to draw that for us. I know it will be incapable, but let me just try to see. Okay, let me come here and say to the exponent of 4, 3x to the exponent of 3, if that is correct. Right, this is what we have. Let me just try to draw the function there. Comparison operator misplaced. Okay, so okay, let me just do this. Sorry. And let's try to draw that. And can I please use an interval so that I can just see what is happening there. Minus 3 and 3. Okay, let me say minus 1 and 1. So this is what I have. This is exactly what we have there. So this is the original function. Let me just try to do this. Yes, very good. So this is the function that we have. And I can draw this function from minus infinity to positive infinity. Let me just do this so that we can see what is happening. So here is our function. Let me just see from Thomas if this is how this function looks like. So let me just do this. This is our function, and there it is, and I can just try to do this so that I can see it. Let's see, x4 minus 4x3 plus 10. But if you just try to stretch this, I think it will be, but this is just the function. Please, let's not beat about the bush. So we are saying compress the graph horizontally by a factor of 2. So we are compressing this by a factor of 2. So when we compress this by a factor of 2, we can just come here and we want to compress this by a factor of 2. So let's just see what Thomas does in that. We multiply x by 2 to get that. So we are just basically going to multiply x by 2. So I'm just going to say 2 times this minus 2 times that, and I try to draw this function. So we are just multiplying everything by 2. So we have x4 and we multiply that by 2. Okay, that is fine. So the formula is obtained by substituting minus 2 for x in the right hand side of the equation. So let me just read this very clearly. We multiply x by 2 to get the horizontal compression, and by minus 1 to give the reflection across the y-axis. So this is already done here. So we are just saying, remember they said compress this by 2, and then they said followed by a reflection along the y-axis. I know reflection along the y-axis, only the value of x changes the sign. So let's just try to do it in here. So what I'm going to do is just the following. So let me just do this. Let me just try to do this. All right, let me start this afresh. Let me just do this, and what I'm going to do here, I see x, and I'm going to start first with compression horizontally by 2. So I'm going to have 2 into 2x into the exponent of 4, and then I will have my minus 4, and then where I see x I'm writing 2. Remember we are here. I'm going to have 4 into 2x to the exponent of 3 plus 10, and just try to find out what I have. So this is compression. You can see that it has been compressed. Now let me just show you the original function very quickly. Let me just show you the original function. Now remember, the original function is x to the exponent of 4 minus 4 was it minus 4? Yes, minus 4 x to the exponent of 3 plus 10. Let me check if this is correct. x4 minus 4 x3 plus 10. Yes, and let me just do this. You see, this is the original one, and let me just use a different color for that. Let me just use black, and let me just use this. So this was the original one. Look, it was more widened, so it was compressed here horizontally, we say. Right, from there in here, now let me reflect along the y-axis. Only the value of x changes the sign. So I'm going to minus, and this is what we have. Now it has been reflected along the y-axis. Is it true that it was reflected along the y-axis? I want you to notice something. Reflection along the y-axis, yes, there it is. It was on this side originally, then it is on this side. So this is a reflection along the y-axis. You can see that this and that. So the function was reflected along the y-axis. So we are so grateful by Thomas giving us these examples, showing us how things should be done. We are so much grateful. So compression horizontally, you are adding in x, and then you are reflecting along the y-axis. Now B, compress the graph vertically by 2 followed by a reflection across the x-axis. So now we are compressing vertically. We saw the compression that is happening horizontally, and now we want to look at what happens vertically. And I want us to look at the difference. When you compress horizontal, this is how it works, and reflect along the y-axis. And then now when you compress vertically, this is what we have. We have 1/2 f at x. So what does this mean? Remember, we have the original function. And where is this function? There it is. We have this original function, x4 minus this. So what is going to happen here? We are multiplying everything here by 1/2. So this is compression vertically. So what I can do in here, instead of doing this, let me remove that. Okay, this is fine. So what I'm going to do now, I'm going to multiply, because they said now we should, in number B, compress vertically by a factor of 2. Compress vertically by a factor of 2, and then reflect across the x-axis. Now when we compress vertically and we reflect along the x-axis, only the value of y changes the sign. We know that's the reflection along the x-axis. Only the value of y changes the sign. And I think we need to go back. I honestly think we need to go back. Now this is the reflection across the y-axis, and this is the reflection across the x-axis. Now, they are saying that we should compress vertically. So let us check. When you compress vertically, you multiply by, for c is greater than 1 over c. So when you compress vertically, you multiply the function by 1 over the value that is provided. So what we are going to do in number B, compress the graph vertically by a factor of 2. So what I'm going to do there is just to multiply by 1/2. So this is 1. I'm going to do this just to be on a safe side, and I'm going to say 1 divided by 2. And remember, you are doing this for every value of x. So I'm also going to come here, whether you do this on the front here or this in this place, the difference does not really matter. So am I correct here? Yes, I am very much correct. So this is what now? This is compressing vertically. I am compressing vertically, and then I am now reflecting across the x-axis. When you reflect along the x-axis, only the value of y changes the sign. So, but remember, when you say minus y here and then you divide throughout by -1, you are going to have this. So what I'm going to do there is just to place a negative there, and here I'm going to place a negative. I have a negative there and I have a negative here. Okay, let me check what is wrong. Okay, I have a negative there and I have a negative there. Okay, let me say -1, and here -1, and now it's fine. Let me just get rid of this one because it looks like it will give us some problems. Let me just get rid of this one. So this is what we have. This is what we have. This is exactly what we have. So we can see this. We can see this. And this was only done for this one. So let us try to do the very same thing for this one and for that one. And then we will come to the end of our lecture. So this is what we have. This is exactly what we have. So let me just come here. Before going there, let me just minimize this. So let us try to come here. And what I'm going to do is this. So what I want us to do is to now deal with this one. Let's do the very same thing. Suppose the question says we have a function this, and we want to compress that horizontally, and we want to reflect across the y-axis, compress vertically, and reflect along the x-axis. So let us just try to draw that function. So we are having, let me just do this, we are having 16. we are having 16x to the exponent of 4 plus 32x to the exponent of 3 plus 10, and I'm going to use minus 4:4. Right, and I'm going to draw that function, and this is the function that we have. This is the function that we have. Okay, that is fine. This is just a function. So what we want to do, in this function that we have is to compress horizontally by a factor of 2. We want to compress this function by a factor of 2 and reflect across the y-axis. And I know compression by a factor, if I compress horizontally, I just multiply every value of x by that. So let me just do it. So I want to compress this by a factor of 2 and reflect along the y-axis. So what I'm going to do, remember how we do that. I just come here to my x, and what I do there, I just multiply this by 2. So I'm going to do this, right? And then remember, I will be multiplying this by 2, multiplying that by 2. And if I reflect along the x-axis, only the value of, along the y-axis, only the value of x changes the sign. And this is what I have. And I want us to notice the difference. I so wish I could have done this on a new graph so that we can see the differences. Forgive me for wasting so much of your time. I'm just trying to ensure that we both understand what is happening here. So let me just leave Jesus. What was the value there? Let me just check. The value was 32. So we have x4 plus 32, x3 plus 10. I think this is what we had. 16, 32, x3 plus 10. Good. So now let me go and do that to the next function. So let me just do this. Let me just copy this and have a new function and paste that. Right, now what I'm going to do here is to compress horizontally by just saying multiply by a factor of 2. I'm compressing by a factor of 2 by a factor of 2. And let me just use a different color here. I'm going to use black, and here we have it, and it was compressed horizontally, as you can see there. But what I want to do there, I also want to reflect that function along the y-axis, and only the value of x changes the sign. And this is what I have. and truly this is the reflection along the y-axis. So this is fine, this is very good. And then secondly, what I want to do, I want let me just go back. Number B, I want to compress vertically by a factor of 2. So what I'm going to do here, I'm going to compress this by a factor of 2 vertically. So I know vertically I have to say 1 over 2, like that. To what? Remember what we do this. We do this to every x value. Let's just come here and show you. We are doing this to every coefficient of x. Every coefficient of x. So let me just do this. So I'm having a coefficient of x, there it is, I'm multiplying by 1/2. I'm having a coefficient of x, there it is, and I am multiplying by 1/2. And let's see what we will have. Okay, oh, there's a mistake there, and this is what we have. And I want you to notice the difference there. Let me just do this. So it was compressed vertically, but now I need to reflect this along the y-axis. Along the x-axis, only the value of y changes the sign, so I will have to multiply throughout here by a negative. So here I'm going to do this by a negative. Oh, sorry, -1. Negative, and I'm going to have a 1 then. And this is what I have. This is what I have. This is what I have. So let me just do this very quickly. So let us try to check what is happening here. I know that the reflection, okay, I can just do this. I know that the reflection along the x-axis, only the value of y changes the sign, but I will have to multiply throughout by -1 in here. So which function am I looking at? Oh god, this is the wrong function. This is the wrong function. Very wrong function. In fact, let me get rid of this because now it's going to confuse me a lot. So let's go here. I just compressed vertically by a factor of 2, and then I am reflecting along the x-axis, and only the value of y changes the sign, but I will have to multiply here by negative. I will honestly have to do that, and then let's check. There it is. There it is. It has been reflected along the x-axis. And let me just do this just to see how things are. Let's just do this. Now let us look at something. Let me remove the negative first so that we can see whether was there any effect. So here it is, right? It was compressed vertically. Now I want to reflect along the x-axis. It has to come to this side because this is the x-axis. So I am placing my negative there, and I'm placing my negative there, and let's check. You see, it was reflected along the x-axis. So guys, I'm not going to solve this one. I will leave this one for you. So please, I will see you in the next tutorial where we will be dealing with exercises 1.2.